What specific problem does the OpenELM method aim to solve in the context of transformer-based large language models?
The OpenELM method aims to solve the problem of inefficient parameter allocation in transformer-based large language models. Traditional isotropic models have the same configuration for each transformer layer, leading to uniform parameter allocation across layers. However, this may not utilize parameters efficiently. OpenELM introduces layer-wise scaling, where each transformer layer has a different configuration, such as the number of attention heads and feed-forward network dimensions. By gradually widening the layers closer to the output, OpenELM enables more efficient parameter allocation across layers, allowing for better utilization of the available parameter budget and ultimately achieving higher accuracies. This method addresses the challenge of optimizing parameter allocation in large language models to enhance performance and efficiency.
How does the proposed method of layer-wise scaling in OpenELM work? Illustrate step by step.
The proposed method of layer-wise scaling in OpenELM works by adjusting the number of attention heads and the feed-forward network (FFN) multiplier in each transformer layer to achieve non-uniform allocation of parameters. In a standard transformer layer with uniform parameter allocation, there are n transformer layers, and the input dimension to each layer is d_a model. The multi-head attention, MHA, has n_h heads, with each head's dimension being d_h equals frac d_a model, n_h, and the FFN hidden dimension is d_FFN equals mcdot d_ model, where m is a scalar FFN multiplier. To implement non-uniform allocation, parameters alpha and beta are introduced to scale the number of attention heads n_h and the FFN multiplier m per layer, respectively. For the ith layer, n_h and m are computed as n_h equals alpha cdot n_h and m equals beta cdot m. By varying the configuration of standard transformer layers using alpha and beta, OpenELM achieves a non-uniform allocation of parameters, allowing for more efficient parameter allocation across layers and ultimately leading to higher accuracies.
What are the theoretical or practical benefits of using layer-wise scaling in OpenELM compared to isotropic models?
The theoretical and practical benefits of using layer-wise scaling in OpenELM compared to isotropic models lie in the more efficient allocation of parameters across layers. In isotropic models, such as OLMO, the same configuration is maintained for each transformer layer, leading to a uniform allocation of parameters. On the other hand, OpenELM implements layer-wise scaling, where each transformer layer has a different configuration, varying the number of attention heads and feed-forward network dimensions per layer. This non-uniform allocation allows OpenELM to better utilize the available parameter budget, resulting in higher accuracies. By gradually widening the layers as they approach the output, OpenELM can allocate smaller latent dimensions in the attention and feed-forward modules closer to the input, optimizing parameter allocation throughout the model. This approach enables OpenELM to outperform existing isotropic models like OLMO, achieving higher accuracy with fewer pre-training tokens, showcasing the effectiveness of layer-wise scaling in enhancing model performance and efficiency.
How is the performance of OpenELM validated or tested across different tasks and evaluation frameworks?
The performance of OpenELM is validated and tested across different tasks and evaluation frameworks by using the LM evaluation harness. This includes evaluating OpenELM on standard zero-shot tasks such as ArcEasy and Challenge, BoolQ, HeliSwag, PIQA, SciQ, and WinoGrande. Additionally, OpenELM is evaluated on tasks from the OpenLLM leaderboard like Arc Challenge, HeliSwag, MMLU, Truthful QA, and WinoGrande, as well as tasks from the LLM 360 leaderboard such as Crows, Pairs, Race, and others. These evaluation frameworks allow for a comprehensive assessment of OpenELM in terms of reasoning, knowledge understanding, and identifying misinformation and bias. The evaluation results are presented in tables that compare OpenELM's performance with other publicly available large language models like Pythia, Cerebras, GPT, TinyLlama, OpenELM, MobiLlama, and Olmo. The results show that OpenELM outperforms these models in terms of accuracy across various evaluation frameworks, demonstrating its effectiveness in natural language processing tasks.
What are the key results achieved by OpenELM in terms of accuracy and parameter efficiency compared to existing LLMs like Olmo?
OpenELM achieved significant improvements in accuracy and parameter efficiency compared to existing LLMs like Olmo. Specifically, OpenELM with 1 billion parameters outperformed Olmo with 2 billion parameters by 36%, while requiring only half the amount of pre-training tokens. This demonstrates OpenELM's superior performance in achieving higher accuracies with more efficient parameter allocation. Additionally, OpenELM consistently showed higher accuracy levels across various evaluation frameworks, showcasing its effectiveness over existing methods. For instance, OpenELM achieved 28% higher accuracy in standard metrics, 36% higher accuracy in OpenLLM results, and 72% higher accuracy in LLM 360 results compared to Olmo. These results highlight OpenELM's success in optimizing parameter allocation and enhancing model performance, making it a promising advancement in the field of large language models.
What are the limitations or drawbacks of the OpenELM method in terms of processing time and efficiency, as identified in the benchmarking results on GPU and Apple Silicon?
The limitations or drawbacks of the OpenELM method in terms of processing time and efficiency, as identified in the benchmarking results on GPU and Apple Silicon, include the observation that OpenELM is slower than Olmo, despite having higher accuracy for a similar parameter count. The primary bottleneck identified in the processing time of OpenELM is attributed to the naive implementation of RMS norm, which results in many individual kernel launches processing small inputs instead of a single fused kernel launch, as seen in optimized layer norm implementations. This inefficiency is exacerbated by the fact that OpenELM has 113 RMS norm layers compared to 33 layer norm layers in Olmo. Although replacing the naive RMS norm with Apex's RMS norm showed an increase in throughput, there still exists a substantial performance gap compared to models using optimized layer norm due to RMS norm not being optimized for small inputs. Additionally, the performance degradation caused by RMS norm was further highlighted when replacing layer norm in Olmo with RMS norm, resulting in a significant drop in generation throughput. Future work aims to explore optimization strategies to enhance the inference efficiency of OpenELM, addressing these identified limitations in processing time and efficiency.